Vector data is easier to go through these coordinate transformations than raster data because raster data, each one of those grid cells has to get a new grid cell value after the transformation. So in this example here, we see the input raster as solid squares in the upper left, and then we see the output raster in the lower right as these squares that are now at an angle to the slide. There's three potential ways that we tend to what we call resample the data. In other words, we want to give that new grid cell, and you'll notice that new grid cell is bigger than the original grid cells. We want to give that new grid cell a value based on either what grid cell it falls into or what grid cells are around it. So in this example here, in the upper right, we see a black grid cell, and with a nearest neighbor transformation, whatever point is at the center of the new grid, which is shown as a dotted line in the upper left, that value is what that black grid cell would get. Or the value of that grid cell would be based on what that black grid cell was that it was transformed from. So the nearest neighbor, it just uses whatever's in the center. It's not looking at anything else around it, but looking at things around it can be useful. In the second example shown in medium gray, we're doing a bilinear interpolation instead of a nearest neighbor interpolation. With the bilinear interpolation, we're accounting for all four of the grid cells shown in either medium gray or black, and we're going to combine those values in some way, maybe take add them up and divide by 4 in order to get a value to put in that grid cell with the dot in the lower right. So we're accounting for more data, and that can be a very useful thing because otherwise we can get artifacts in the data. The nearest neighbor resampling is famous for ending up with a new raster grid that has artifacts associated with it, especially if you're doing something like a digital elevation model, where each one of those grid cells would represent the elevation at a certain point. With the cubic convolution, we're just taking a bigger neighborhood. Instead of a 2x2 neighborhood, we're taking all of the grid cells that are shown in the upper left in light gray, medium gray, and black, and we're taking the values of each of those grid cells, let's say once again the elevation from a DEM, and let's say we're averaging those. We're adding them all up and dividing by 16 in order to get the new value that's going to be associated with that one grid cell in the lower right. The way that we actually do those values, the z-value for elevation, we could find in several different ways. That just taking the mean or the average would be one way, but we might also want to account for what the actual distance is to that center point of the grid cell, and that would result in a more complicated equation. But the idea is the same. We just want to find we want to estimate what the elevation would be at some intermediate value between the centers of those grid cells in order that we might assign a value to this newly transformed grid cell.